which I am going to discuss, and how it kills like the current effort to make a counterexample for the slice conjecture. So it's kind of a sad story, but anyway, we move on. Yeah, so I think every knot theory talk with a sufficiently general audience starts by defining what is a knot. Hopefully everybody knows, but if you don't know what is a knot, it is an. I mean, in real life, if you think knots are tangled lines, but mathematically, we close them up. So when I say a knot, they're always embeddings of a circle into three sphere, can be knotted, and we also want them to be smooth because for the entire talk, I'll be doing everything in the smooth category. Great. So given having defined knots, so now we know what knots are. We have to classify them. And in fact, this trying to classify knots comes from a very weird notion of how the world is consisted of from Lord Kelvin. He thought that the world is consisted of knotted loops of luminiferous ether, and therefore by classifying all possible way of knotting a circle, you can realize you can study the world itself, which now we know it doesn't really make much sense. But that's how knot theory came out. Okay, so in order to study knots, one of the most classical things to do is to consider smooth orientable surface inside the three sphere bounding your knot. Those are called Seifert surfaces. There are a lot of them. So given one knot, there are so many Seifert surfaces that can possibly bound your knot. But by studying their topology, we can come up with a lot of very classical knot invariants. For example, the signature, which comes from the Seifert form. And then you have a Alexander module, which gives you the Alexander polynomial. And so these are the Seifert surfaces, which are quite pretty, isn't it? Okay, so nice thing about this Seifert surface is that, or bad thing is that they usually have a lot of genus. If your Seifert surface has no genus, then if it's a disk, then it just means that you're not bounds a disk inside the three ball. You can isotope it across the disk to untangle your knot into a simple circle. So which means that if your knot bounds a Seifert surface of genus 0, then your knot is unknotted. But now we want to twist the question a little bit and say S3 is now a smooth boundary of the Bohr ball. And you think about, instead of thinking about surfaces inside the three sphere, we now think about surfaces inside the Bohr ball, smoothly embedded. And then you ask the question of what kind of surfaces are there. And that notation, by moving from the 3-dimensional to the 4-dimensional notations, gives you knot concordances, the theory of knot concordances. And if your knot defines a disk inside the Bohr ball, we say that your knot is slice. Okay, so we can define, that gives you a definition of smoothly sliced knot. Your knot is smoothly sliced if it bounds a smoothly embedded disk inside the Bohr ball. There are a lot of non-trivial sliced knots, which makes it very different from the 3-dimensional setting. So for example, probably the most elementary examples are that if you're given any knot, you take its mirror image. And in fact, you also have to reverse this orientation because not connected sum operation is defined for oriented knots. But anyway, if you take those copy and connected sum it with the original knot, then the knot that you get is always sliced. It always bounds a smoothly embedded disk inside the Bohr ball. A very intuitive way to see this is by spinning your knot. So knot is a closed circle, but we split it open a little bit and say that it is tied to an axis in which it is going to spin. And then you spin your knot half times, then your 3-dimensional space becomes a 4 ball as well, And on the boundary, you have this knot, which is your original knot, and on the opposite side, you will have minus k, but then it'll go through a disk, which gives you a sliced disk of your knot. Yeah, so there are a lot of smoothly sliced knots. There are even much more knots which are not sliced. And then that gives you a question of, instead of classifying knots, let's try to classify which knots are sliced. Which knots, given any knot, like you have to answer whether that knot bounds a smoothly embedded disk inside the four-ball. This question is obviously much easier than classifying all knots, but this is still very hard. And the main reason is that there's not much things that you can do. Intuitively, you might think proving your knot is not sliced might be harder because you're proving that something hypothetically doesn't exist. But there are a lot of obstructions that exist right now, like signatures. There's a condition, an Alexander polynomial called the Fox-Miller condition. And then there's so many other things. But if you think your knot might have a good chance of being a slice, the only way to actually prove that it's slice is by constructing one. There's no indirect way for now. And therefore, asking whether a random knot is slice is a very, very difficult question, especially if it looks like slice. Yeah. And this thing is even harder because in order to prove that your knot is slice, as I said, you have to construct a disk, and disk is embedded in the four-ball. So you had to somehow visualize some embedded surfaces in the four-ball and prove that your surface bounds or not. And it is not immediately clear how do we construct them. So for example, this knot is slice. It is very non-trivial. It bounds a slice disk. And if you ask, can you draw a slice disk inside of this knot embedded in the four-ball? It is not immediately clear. And how do we do this is by doing Morse theory. If you have a smoothly embedded, our surfaces are smooth, and they're smoothly embedded, and therefore there is an ambient Morse theory. Any smoothly embedded surfaces consist of 3 elementary pieces. So here you have a burst, unknot component is suddenly created, and then here you have a death. Unknot component, which is separated from all other components, can be eliminated. And in the middle, you will have a lot of saddles. Saddle is a local move, like going from this one to this one. You're adding a square. It can merge 2 components into one or split 1 component into 2. By composing these elementary cobordisms, you can explicitly construct this slice disk. So for example, here's something called a Kinoshita Terasaka knot. How you construct a slice disk of this thing is to just add 2 bursts, isotope in a magical position, and then you do one saddle, and then bam, you have a Kinoshita Terasaka knot. It bounces slice disk with 2 bursts and 1 saddle. And a really nice thing about this kind of construction is that it is even more visualizable because it has no deaths. They are very special because if you have a disk, we call them a ribbon disk. So if you have a ribbon disk, so it has no death, then what you can do is you can even draw it in the 3 dimensions, in the 3 sphere, the boundary. So for example, the slice disk for the Kinoshita Terasaka knot that I constructed here can just be drawn like this. So the rule here is that this is an immersed disk with only singularities or something like here. This is a local picture. It's called the ribbon singularity. And whenever you see them, you can perturb one side into the fourth dimension to get a ribbon disk. And so these are the very, very good knots. And we say that a knot is ribbon if it bounds a ribbon disk. So a knot is ribbon if it bounds an immersed disk with only ribbon singularity inside S3. So it looks something looking like that. Obviously, ribbon disks are smooth disks, so ribbon knots are sliced by definition. Then you can ask the reverse direction. If you have a slice knot, so you already know that your knot bounds a slice disk, which might contain a lot of depth. You can we always find another disk which has no depth? So to abbreviate, we're asking, are slice knots always ribbon? This is the slice ribbon conjecture, asked by Ralph Fox in 1962. And this is very important because if it is actually true, then it is somehow we're making some purely four-dimensional, smooth four-dimensional topology into a purely three-dimensional setting, which is very, very unlikely to happen. And therefore, many people think this might be false. I'm one of them. If you think it's true, then I respect that. But anyway, I'm on the team false, and in fact, I think most smooth conjectures in smooth four-dimensional topology should be false. It is a bad world. Nothing really works. So, but if you firmly believe something is false, you have to start trying to find a counterexample, and that's how things work in our field anyway. Okay, so how to find a counterexample? There can be two ways. The conjecture is that slice knots are always ribbon. So you might try to find a knot which is ribbon, slice. So you might try to find a knot which you already know not to be ribbon. And then if you can prove that it is sliced, then that's it. Then that'll be a counterexample. And one of the earliest and probably the biggest family of such examples were given by Miyazaki in his work in 1994. His construction is very general. You start with a knot which is negatively amphichiral, which means that if you take a mirror image, it can be isotoped to the original position, but with the orientation reversed. And it also have to be fibered. So the complement is fibered over a circle, and then it should also have an irreducible Alexander polynomial. If you have such a great knot, then you take an even comma one cable. So basically, you duplicate it into even number of strands, and add one like partial twist. Then the theorem is that it is never ribbon, but it kind of looks like slice. So this is not a mathematical opinion, because what does it mean? What does it even mean by something looks like slice? But a very vague way of explaining why is that if your knot is negatively amphichiral, its concordance inverse is mirror image. So if you take the k connect sum k, so take a connect sum of even copies, then it will be slice. And you're taking even number of strands. So it kind of looks like two n copies of knots stacked to each other. And then you might think, oh, that kind of looks like slice. And if it's convincing to you, that's good. Okay, so that gives you a family of potential counterexamples. Some people thought it's slice. I don't know. I did not. Anyway, so what is the easiest, the simplest example in this family of potential counterexamples? There are a lot of conditions, but these are all satisfied by this knot, the figure 8 knot. It is even strongly negative amphichiral, and then it is fibered. Alexander polynomial is irreducible. So, and the smallest positive even number is 2. So the question reduces to whether 2,1 cable figure 8 is not a slice. And surprisingly, this kind of question goes back even much further than Miyazaki's work in 1994. This question appears in one of the unpublished manuscripts of Akio Kawauchi in 1980. And it has been open ever since until 2022. Okay, so what are the main results? The first step was that using some toolkits in eager floor theory, which I'm gonna very vaguely discuss, and we have proved that this simplest thing, the 2-on cable figure, it is not smoothly sliced. But that was not all. Then things made an interesting turn. Then, instead of figure floor theory, which had the clear limitations that I'm also going to discuss, we changed our strategy. Instead, we used real cyber theory developed by Hokuto, Masaki, and Miyazawa. To as a first step, we show that if your cabling parameter is of the form 4n plus 2, then it is also not smooth, not slice. And finally, earlier this year, we were able to prove the most general case. In the case of figure 8, we proved that any even comma 1 cable is not smoothly sliced, and in fact, it has an infinite order. Okay, so they are the main results. And then let's briefly before going to like proof strategy, let's briefly discuss about why this has been difficult. It has been open for 42 years, so there has to be a reason. So the brief reason is that algebraically it really looks nice. So first of all, it is algebraically sliced, and if your knot is algebraically sliced, almost all the topological invariants vanish. And then it also bounds a non-homologous disk smooth disk inside this complex projective space, minus with a puncture. So CP2 and its reverse minus CP2. And once this condition is satisfied, then it works from a work of Vanilescu, Willis, Marangon, and Sarkar that S invariant, which comes from Kovanov homology, also vanish. So Kovanov homology cannot be used. And finally, it is something called rationally sliced. Rationally sliced means that if you change your four-ball into something weirder, so some punctured smooth four-dimensional manifold whose homology, Q rational coefficient singular homology is the same as four-ball, then you're not actually bound some smooth disk. This follows from a very nice argument of Akio Kawauchi in the same manuscript, and it goes as follows. Figure 8 is not just negatively amphichiral, it is strongly negative amphichiral. So S3 admits a orientation reversing involution in which setwise fixes your knot. Okay. And that in this setting, you do an equivariant zero surgery along your knot. And then the involution becomes free. So what you do is that you take a zero trace. Probably I should use some blackboard. So what you do is you take a four ball, and then you take a two handle attached to your knot equivariantly along the framing 0, aka Seifert framing. This is a smooth four-dimensional four-manifold, and its boundary is the zero surgery. And you know that the involution is now free. We can identify the boundary with respect to this involution. The result is a rational homology four-ball with H1 equal to Z2. And here you can immediately see you're not bounds a disk because this is a two handle, so it just bounds a disk like that. Okay, so it is rationally sliced. And once you have that, it kills almost all known floor theoretic invariants. Although also all the cyberwritten invariants as well, almost all. Okay, so that gives you the question of, so there's so many invariants that vanish for these examples. What invariant should we use? And our vague idea starts from this kind of strategy, which is kind of classical. You have a knot. Instead of doing some surgery or something, you take its branch double cover. You remove the neighborhood of your knot, take a double cover, and then you glue a solid torus back in. That is a free manifold, right? It's a rational homology sphere. So the nice thing about this construction is that this also works in the four-dimensional way. if you're not bound the disk, then you can also take branched double cover, not along S3, but of 4 ball with respect to your disk. That gives you again a smooth smooth rational homology ball. So the obstruction becomes as follows: if you have a knot, and if you can show that branch double cover does not bound a smooth rational homology ball, then your knot is not sliced. And this looks very simple. This is a very simple strategy, but it's also a very powerful strategy. For example, the sliced ribbon conjecture for two bridge knots were proven explicitly in this way, and it was enough. And usually, like this obstruction are carried out using some gauge theoretic way or some like Donaldson diagonalization theorem or something. So we have a very nice and simple strategy. The problem in this case is that such a full manifold does exist, so it's not going to succeed. And why does such a full manifold exist? Is because the Montesino streak. Okay, so what is a Montesino streak? It's not just for figure 8. If you have a knot, any knot, not just figure 8, you take a 2-1 cable and you take a branch double cover. It is diffeomorphic to the +1 surgery along K connects on K reverse. K reverse means that you're not, but the orientation reversed. Okay, so, and this is kind of explicitly what's happening. So I draw figure 8s here, but you can just replace with any knot. You take a +1 surgery, and you take a quotient with respect to this rotation action. Then it becomes a 4 ball. And if you draw the image of the fixed point set, it becomes a 2-1 cable. Okay, so that's the Montesino streak. In the case of figure 8, what happens is that figure 8 is reversible. It's isotopic to its orientation reversed. So this one is nothing but 2 copies of figure 8. And figure 8 is negative amphichiral, so it is sliced. And therefore, this knot is sliced, so you can do Dane twist, +1 surgery Dane twist along your disk, which gives you a contractible smooth manifold, bounding this manifold, this surgery, which is diffeomorphic to your branch double cover. So it fails. And so we have failed, so we have to learn something from our failure. So the first thing that we learned here is that probably we also have to keep track of the deck transformation. So the idea is that in our construction here, the branch double cover, it also comes with a deck transformation, which is a smooth involution, orientation preserving. And this sigma of D, the branch double cover of B4 along the disk, also has a deck transformation, and it restricts to the deck transformation on the boundary. So we can take that as our second try. So if you're, for your given knot K, if your branch double cover bounds a smooth rational homology 4 ball, so if your knot is sliced, then it bounds a rational homology 4 ball where the deck transformation extends to a smooth diffeomorphism. Which means that if you can show that the deck transformation doesn't extend smoothly for any rational homology 4 ball filling of your branch double cover, then it follows that your knot is not sliced. And again, this strategy fails again. It fails because it is rationally sliced. If you take a 2-1 cable, it becomes something called a strongly rationally sliced, and in this full manifold. And then once your knot you have a strong rational slice disk, you can do a branch double cover along that, which gives you the smooth rational homology ball with the extension of your deck transformation on the boundary. So what we learned here is that probably we need more structure. These are just vaguely rational homology 4 balls. And if you think about this example, the thing that here is that it is not spin. So having learned that, here's our third try of trying to obstruct its sliceness. So if your branch double cover does not bound any smooth rational homology oval such that the deck transformation on the boundary extends to some diffeomorphism in the interior, and also it carries this diffeomorphism invariant spin structure, then you can prove that your knot is not sliced. And luckily, in our first try, this could be detected using various symmetries in Higger floor homology, which led us to our first paper. Okay, so very vaguely, what happens is that Higger floor homology is a package which, for integral homology sphere, of course, is defined in a much more general sense. But in this case, it gives you integer graded F2U module called HF minus of y, where U is a symbol of degree -2. And this comes with this two symmetries. So first one is charge conjugation. It's called a charge conjugation is because that's what is already defined in the cyber-written sense. And that it exists because y has a spin structure, unique spin structure. And if you have a diffeomorphism, which is orientation preserving, and in fact, you can just say it's a mapping class because it's up to isotopy, then there's a well-defined action on HF minus. And that is going to be our extension of our deck transformation. So our algebraic obstruction becomes something like that. If you can prove that there's a degree 0 element inside the HF minus of branch double cover, which is invariant under these two involutions, and also is local, I'm not going to explain what it is, then your knot becomes knot slice. Nice thing about Higger floor homology is that they're all computable. There is a very computable, it is in fact a computable model of cyber-written theory. So, and using this observation that this branch double cover can be computed as a +1 surgery, and in fact this diffeomorphism is equivariant, and also Higger floor homology has a nice surgery formula. Therefore, we could just compute everything explicitly. Just see our paper. Everything is computed explicitly, and show that such element in fact does not exist. That's our first way of proving that this knot is not slice. Okay. Of course, the story is not over because this is a bad strategy. The upside of this is that it has a very nice flexibility. Here, we only discuss with figure 8, but even if it's not figure 8, some other knots, this process is very computable. In fact, it is not written anywhere, but what is true is that for half of all possible knots which are torsion in the knot concordance group, you can do the same thing and prove that 2-1 cable is not slice. However, if you stick to the figure 8 knot, then this is really bad because this process depends on the computability of branch double cover as a surgery. This only works if your cabling parameter is 2. For example, if you take the 6-1 cable and then take a branch double cover or branch whatever cover, then you have no idea what that manifold is. And then you're in trouble because you don't even know your manifold. What exactly are you trying to compute? So we need some completely new strategy, which came from a work of Aceto, Castro, Miller, Park, and Slipstitch, which is in fact goes back to even the previous work of William Bollinger. What they construct is that there is a smooth annulus inside the connect sum of two copies of CP2 with two punctures, and you draw on the one side you draw the 2-1 torus knot 2n, 1 minus 20n. And on the other side, you draw the 2n, 1 cable figure 8. What they proved is that they co-bound a smooth annulus. And how they construct this is simply by taking a cable of this concordance. Here's a zero-framed figure 8. You isotope into this magical position, and you draw these two red hoops and add -1 full twist. in terms of Kirby calculus, what you're doing is that you're adding copies of CP2 into each of the pieces. So now the ambient space is 2 CP2. Okay, now if you add -1 full twist here and there, it becomes an unknown. With the caveat that your framing changes. You start with a Seibert framing, then you end up with a -10 framing. But anyway, so therefore by taking the 2n,1 cable of this concordance, you get this surface Cn. And what you're going to do is that you first assume that this is smoothly sliced. So you cap off this boundary with some hypothetical slice disk, and try to derive some contradiction. Okay. And it's probably worth mentioning here is that this, as I said, their paper, this construction goes back to work of Bollinger. He tried to study configuration of spheres in NCP2, and while doing that, he was considering the following untwisting sequence of twist knots. You start with a twist knot with n half twist. You isotope like that, and then you draw a small hoop here and add a -1 full twist. Then it becomes like that, and the number of half twists decreases by 1. Okay. And figure 8 knot is a twist knot. That's what happened. Okay, given such a surface, so you have a surface in 2 CP2 bonding your cable. Its homology class is 2n,6n. We want to do branch cyclic cover. And after doing branch cyclic cover, we want it to be equivalently spin. In order to make sure that it is spin, the algebraic condition is that the branching parameter should be divising your homology class, and the quotient should be odd. So it means that, well, if you count the number of 2's dividing your n, so let's say 2n is 2 to the power of k times odd number, then you have to take 2 to the power of k fold cyclic cover. We denote that as w, and then it'll have a deck transformation called tau. Then what happens is, as I said, tau has order 2 to the power of k, and then your full manifold carries a unique tau invariant spin structure, which is a perfect setting for applying something called the real cyber-rhythm theory. I'm not going to explain what it is, because it is one hour talk anyway. But using cyber-rhythm theory, what you can define is something called the kappa invariant. It is a real analog of what happens in pin-2 equivalent cyber-rhythm theory. Manolescu, in his earlier works, defined kappa invariance using pin-2 symmetry in cyber-rhythm theory. By replicating what he did in the real setting, you get a rational number, which is in fact integer divided by 16. And you define it for any 3-manifold spin with symmetry. So here we take this kind of input. So you take a boundary, so branch cyclic cover of S3 along your knot. You take a unique spin structure, and you take a involution. It has to be an involution. So you take a tau to the power of 2 to the power of k minus 1. And that gives you a well-defined rational number, which we call it a higher kappa invariant, which is a little bit misleading, because as this parameter k increases, it kind of contains less and less information. Well, higher doesn't always mean good, isn't it? Okay. Okay, and so having defined this invariant, we need some obstruction. We need some inequality. That comes from something called the 10/8 inequality, which is, again, a real analog of what happens in the pin-2 equivalent setting. This idea of using 10/8 inequality to do to obstruct knot slicing it was initiated by a paper of Andrew Donald. And then, so we're basically trying to do their strategy, but in the real setting. Anyway, this is our inequality. You have a lot of homological data, like the signature of a branched liquid cover, and you have a B2 plus of a 2K fold cover. You take a subtract. You have to subtract the B2 plus of the 2 to the power of K minus 1 fold cyclic cover, and then since we're in a relative setting, we have a boundary term, which is exactly our higher kappa invariance. And then you'll have some brownie point here. This thing is not free. In general, you cannot add anything into this inequality. But as in the Pinto equivalent setting, in some special cases you can. And what you're going to use here is the fact that if your K is something called a K strongly spherical, and this term is bigger than this, then you can freely add 1/2 to your inequality, which turns out to be really necessary. Okay, so what does it mean for not to be strongly spherical? It means that the higher real cyberwritten spectrum is spherical. More precisely, it should be a one-point compactification of a complex representation sphere. In this setting, this is kind of L spaces. Like your spectrum is as simple as possible. So in this setting, what you're saying is that this R, the complex dimension, is basically minus the kappa invariant. So you can read off everything from the exponent. Okay. The first lemma is that we need our knots to be strongly spherical. The only boundary knot that's appearing here is the torus knot. The torus knot of the form 2k times odd number, comma something. We want it to be k strongly spherical. The answer is yes, and that's our first lemma. And that is, the proving that comes from an earlier work from 1990-something of Mrówka, Uszpat, and Yu. What they did is that if you have a Seifert rational homology sphere fibered over a sphere, such that the canonical spin-C structure is self-conjugate. In this setting, they construct a one-to-one correspondence between the irreducible solution to the monopole equation and the solution to the vortex equation. So more precisely, a part of their work is that if you choose a metrics and connections very, very nicely, then the irreducible critical points of the Chern-Simons Dirac functional correspond bijectively to this kind of thing. I'm not going to, so I'll not explain precisely what they are, but you can intuitively, C plus of E are kind of holomorphic orbifold divisors, and C minus are anti-holomorphic divisors. Okay. So if we can prove that the action of J composed with tau, J is the quaternion element of Pinto, and tau is the involution in the spin sense. If you can prove that this action swaps them, then if you take the fixed point spectrum, then they will all vanish, and you're only left with a reducible solution. So we'll know that it is a complex sphere. So we have to prove that. But what we already know is that J is anti-holomorphic, and therefore it already swaps them. So if tau is holomorphic, then it will imply that it fixes the holomorphic divisors and fixes setwise, and also set the same for anti-holomorphic things. So that is the thing that we have to prove. The action is holomorphic in the quotient orbifold. It looks like this. This is a complex, the quotient orbifold. You have the cone point of order 2 to the power of k times m, and you have a 2 to the power of k number of cone points of order q, and they will be permuted by this deck transformation. The action is obviously holomorphic here, and near this singularity, the action is linear, and therefore it's also holomorphic. And therefore it's holomorphic, and therefore your torus knot is now proven to be strongly spherical. But it doesn't tell you much things about what is the exact value of this. You know that now this real cyberwave spectrum is a complex sphere, but it doesn't tell you about which dimension it is. And so in order to compute its exact value, you need a completely separate argument, which comes from our argument back in 2024, which is based on something called the Dye-Satire-Tophergen lattice homotopy type. And in order to carry out that argument, we start by drawing a plumbing graph, whose boundary is your 2 to the power of k fold branch covers torus nut, which is a rational Briscoe sphere. So what is a Z2? What is a deck transformation? So we have 2 to the power of k identical legs, which corresponds to these identical singularities. And this deck transformation obviously permutes them cyclically. Okay. So given that, the twofold symmetry given by taking as 2 to the power k minus 1 power will be also like swapping those identical legs. And once you have this twofold symmetry on your plumbing graph, you can induce a Z2 action on the lattice homotopy type. So the lattice homotopy type is looking something like that. And how this I basically acts is it swaps the left side and right side, which means that for this action on the lattice homotopy type, the fixed locus is a sphere of dimension exactly the Neumann-Ziebenmann invariant for the spin structure. That's nice, but we could not prove that cyberwritten floor spectrum is exactly like equivalently homotopy equivalent to this lattice homotopy type. What it could do is that at least there is a homotopy equivalence which is an O2 equivariant map. And basically we're trying to do Z2 fixed point spectrum. And the domain and codomain are finite spectra. That ensures that the induced map between the fixed point set with respect to Z2 action is a two-adic homotopy equivalence. One of the nice things about p-adic homotopy equivalence is that it induces isomorphism on ZP coefficient cohomology. So what we have learned is that the cohomology of this real cyberwritten spectrum is the same as the cohomology of the complex sphere, which comes from a fixed point of the lattice homotopy type. So we know that it is supported, the cohomology is supported exactly at this degree. However, we also know that this is a complex sphere. Therefore, you know that its complex dimension is exactly this. Therefore, we conclude that the higher kappa invariant is exactly that, the minus half of the Neumann-Ziebenmann invariant. Now we have to compute it. It is also a different story. We go back to the plumbing graph, but instead of having an abstract ray, we have to actually compute compute all things in the plumbing graph. For this specific thing, your plumbing graph looks like this. This leg just has one node, and the identical nodes are the identical legs are -2 and -3 and -2s. Okay. In order to compute the Neumann-Ziebenmann invariant from a plumbing graph, you need two things. One thing is signature. The other thing is the square of the spherical Wu class. So the spherical Wu class is supported on this node and exactly half of these nodes, which gives you that the Wu square is exactly this, 2 to the power of k minus 4 to the power of k times n. Then you also need a signature. However, this tree is negative definite, so signature is B2. You just have to count the number of nodes. There are exactly this number of nodes. Then the formula is signature minus Wu square divided by 8. If you do that, m vanishes. And then mu bar invariant becomes exactly -2 to the power of k. k minus 1 to the power of 4. And by taking its minus and dividing it by 2, you get the exact value of the kappa invariant to the power of k minus 1 plus 1 over 8, which is very surprising because it's so simple. And so that's the starting of this computational miracle. You also have to compute all these homological data. So what you have to compute the B2 plus of 2 to the power of k cyclic cover to the power of k minus 1 cyclic cover, and also signature of the 2 to the power of k cyclic cover. And you have to check whether this value is bigger than that, because we need the Brownian point. And these are, this can be computed from something called the G signature theorem. Packaged into a nice lemma, it looks something like that. If your n is a prime power and divides your homology class, then here's your formula. You start with a B2 plus of your original manifold, the genus of your surface, self-intersection of your surface, and then you have something called sigma n of your knot. Sigma upper n is defined as a sum of the values of the Levin-Tristram signature over all nth root of unities. And that's, in general, very hard to compute. However, we're in a very special case, which allows us to do some brute force computation. It's an ugly thing. So we only compute. So here's the result. For these kind of torus knots and prime p, the sigma p of this torus knot has this formula. Using that formula, we can plug it into this formula and compute all the homological quantities. It turns out that B2 plus are 2 to the power of k plus 1, 2 to the power of k minus 1 plus 1, and this signature is 2. Now you plug in. Your inequality becomes this. But it's weird, because all the powers of 2 cancel out, and all these integers also cancel out. You're left with 1 over 2, which we freely get, because this is always bigger than that. And then everything else is now canceled out, so your inequality becomes 1/2 is less than or equal to 0, which is a contradiction. And here, that's why we really needed this extra 1 over 2, because otherwise we'll get 0 and 0, which will not give us anything. Okay, after all these computations, we got a contradiction. And therefore, any even cable of figure eight is not smoothly sliced. Actually, you can do more. You can flip the concordance that we used, the Cn, and take their kind of connected sum to get a concordance in 2kCp2 between k-fold, like C-fold branch connected sum of cables of figure eight and the connected sums of torus knots. The same inequality will apply, and again, every term will cancel out. Therefore, we'll end up with the same inequality, which violates the reality, and therefore, you can say a little bit more. The even cables are not just smoothly sliced. It has infinite concordance order, which means that if you take many copies of them and take their connected sum, they're still not going to be smoothly sliced. So that's our main result. And the story is basically done for figure eight. Okay, so let's end with some remarks. That if you go back to this 10 over 8 inequality, where is it? Yeah, this 10 over 8 inequality, we had a lot of things, and in general, we don't expect it to be exactly equal with no extra term. But it turns out that for any even cable, take cable and take branch cover, and if you compute all the quantities, it turns out that it is always an equality. We suspect that there might be some geometric property of this. This might come from some special geometric property of this smooth concordance to start with. This concordance from 0 frame figure eight to the -10 frame dot knot it might have some very special properties. And that we suspect that this might be the key to generalizing this result to like all Miyazaki's examples. Because for now, this is such a miraculous cancellation, a miraculous untwisting sequence. It basically only works for figure 8. If there is an algebraic general criterion for that same argument to happen, and it turns out that Miyazaki's knot, this figure 8 knot is basically the only one that this argument applies. But if you really understand why this is happening, we might be able to generalize this to other knots as well. Okay, and that's all. Thank you very much.
Are there any questions or comments?
Thank you for a nice talk. And I wonder how computable is the real cyber-Wheaton invariant for knots? Apart from the 2n1 cable of figure 8, are there any other?
So they are in general extremely uncomputable. Basically you cannot compute anything unless it is a very simple coarse knot, like something like that. Yeah, there is a plan, like ongoing group work with Masaki, Masaki and Zhongwan about making it much more computable, but for now it's very uncomputable.
And does this invariant have some factoriality?
Yeah, like there's a Bauer-Furter invariant. So if you have a 4-dimensional cobordism, you can associate to like a map between cyber spectra shifted by indices, direct indices. And the gluing theorem says in many cases that it is functorial.
Okay. So it's also a concordance invariant, or
like kappa is a concordance invariant. Like most invariants that you can define in cyber theory, it turns out to be concordance invariants.
Okay, I see. Thank you.
Any other questions? You wrote SWF. F is a floor. Cyber floor theory is.
No, SWF is a cyber spectrum, which is a spectrum valued invariant.
So do you use analysis or just combinatorial?
Analysis is already done in previous works of so we had all sorts of these functorial nice properties.
Any other questions? Let's thank the speaker again.